the left. And so trying to find my mouse. I can't. But anyway, so you see on the bottom the RF piece, and then you see the typical FFT in the receiver, digital beamforming, resource element demapping, equalization, demodulation, descramming, and decoding in the receiver side, right? So this is a processing chain of a 4G or 5G system at the base station, right? And depending where you put the split, so if you put the split at 6, you do the entire physical layer in the RU. If you use a split option of 8, then you just do the analog part in the RU, right? The analog part in the converters in the RU, and all the digital processing is done in DU. So why does it matter? Well, if you keep the RU very, very small, it's probably easier to develop multiple RU options, and it gives you a lot of advantages for your software, right? Everything else can be done in software and implemented on a DU. So it makes the RU very simple and maybe swappable for other RUs, right? It's easy to extend functionality because everything is done in software on DU. And it's also easier for multi-vendor interoperability, right? Because they all just rely on analog digital converters. You can think about USRPs, right? Are you familiar with USRPs, the software radios from NI? They have a digital analog converters, right? And they have an FPGA, and then they have some RF processing. So this could be like a split 8 implementation. If you hook it up to a computer, everything else runs, all the software, entire protocol runs in the computer. Okay, so to give you a little bit more context, 3GPP essentially, as I said, it identifies all the split options, but it actually uses only option 2 in most cases, right? You have the PDCP on the left side in the central unit, and you have the distributed unit where you have everything else. But this coincides with a small cell forum in the middle, and with ORAN, right? Remember, ORAN leverages option 2 for its higher layer split. And now if you look at CRAN, if you remember CRAN or Cloud RAN, they introduced something called the remote radio head, which had ADCs and backs and the RF processing. So this was according to split 8, and everything else is centralized. And now if you compare this small cell forum architecture and ORAN, what do we see as a difference? Well, the small cell forum uses option 6 for the lower layer split, and ORAN uses option 7.2, sorry. So what does it mean? So when we put more functionality in the RU, like the small cell forum does in the middle, and then the connection between the RU and DU is less stringent, right? As you process the data on the receiver further, you reduce the throughput, the bandwidth you need, right, on your connection, on your interface. But if you do the RU more lightweight, right, include less functionality in RU or more in a DU, you enable more flexibility because everything is software defined. However, you have more traffic going through this interface. So let's talk a little bit more about the architecture, about ORAN. So we have these different protocol layers, right, in cellular communications, and I introduced the ORU, ODU, and OCU. And the OCU can be split in the control plane and data plane. So in addition to that, ORAN introduces 2 new components called the non-real-time and near real-time RAN intelligent controllers. So these are quite interesting and have not been existing before. And it has a bunch of interfaces to connect these components. And what you see here on the top, those are new interfaces that are actually open, meaning that people can use components from different vendors. And it also means that you don't have to build the entire processing chain by a single manufacturer. So you can use the ORU from one vendor, the ODU from another vendor, and OCU from yet another vendor if you want. So vendor diversity and interoperability is supposed to be enabled with this. So if you look a little bit more details, what has ORAN on the bottom in the middle, you see the distributed RAN. You see the RU, which connects to the users right on the bottom. The RU has an interface to the DU, and the DU has an interface to the CU. So this is a distributed RAN. On the top, we see the near real-time RIC and non-real-time RIC, as I mentioned. And then, of course, there's a backhaul on the right, but this is anyway available even without ORAN. So let me give you a little bit more details about the different pieces. On the very top, what we've seen in the previous slide is the RAN operation support system. It is quite common now in modern and software-defined wireless networks. It helps you with radio planning and testing. It also features the service management orchestration, the SMO, which has a lot of components you can see here. Among them is the non-real-time RIC, which is the new feature of ORAN, and we'll talk about it in a minute. So it helps you to do data analysis, logging, and inventory certification. So all the network operators, they collect a lot of data here, right, and analyze it to optimize the network and services. Then we have the RAN intelligent controllers. One is actually featured in the SMO, which is the non-real-time RIC. So the non-real-time RIC operates at a time scale of 1 second or more. It could be minutes or hours. And then in a real-time RIC, which is connected to the RAN directly over the E2 interface, we have the control that can operate within 10 milliseconds to 1 second range. So it's not really real time, but it's close to real time, near real time. So what are xApps and rApps? These are microservices. These are kind of applications that help you implement algorithms or features to optimize your RAN services. So the xApp stands for Extended Application. It can be provided by third parties, so third parties to the operator, right, and a new industry member or anybody else, really. They're hosted in a near real-time RIC. What they usually do, they collect data from the RAN, they process the data, and then send some control actions to the RAN to optimize the service. So what are some of the examples of xApps? Well, you can do some scheduling control. You can configure the scheduler or change the scheduler maybe, right? Or indicate that the MAC layer should execute a different scheduler. It can do traffic shaping and handover management as some examples. And we'll see some actual real xApps later on today. What are rApps? Well, those are called R for remote applications. They're hosted in non-real-time RIC, and they support RAN optimization operation at a lower time scale. They can do they can derive control and management policies that operate at a higher level, and the RAN operations and users can leverage, right? Examples include frequency management, network slicing, and policy management. So network slicing can be either an rApp or an xApp. So there is a lot of opportunities here to implement it, either the very slow scale, right, in terms of minutes, or at a near real-time scale in terms of hundreds of milliseconds, maybe.
Sorry, okay, what do you mean by traffic shaping in the near real-time RIC?
Yes, so you will try to essentially see how the traffic flows, right, and which cells are overloaded. If you have a crowded event, right, and then they're all near one cell tower, near one RU, right? So that will cause maybe an imbalance between your capacity of the different cells, right? One cell will be overloaded at capacity maybe, and maybe running out of capacity, and surrounding cells may not have users. So you can potentially try to shape this traffic across different cell towers by dynamically maybe increasing, the cell coverage, right, or the beamforming, and maybe sort of moving users to other surrounding cells to improve the capacity. Does it make sense?
Yeah, thank you. And can we, in this situation, for instance, in 5G, to kind of movement of resource from the other base station to this one? I mean, computational resource or even bandwidth.
Yes, that is facilitated from the virtualized environment itself. Yes, absolutely, because all these functions could be virtual machines, right, that run on servers. So you can potentially manage the computing resources and allocate different resources, different units, right, as you need them. And that's actually a great point, because you may need more processing for some specific services, and because it's now being very prioritized or very demanded, right? And less processing for other services, and maybe also because the channel is worse in one situation than in the other. Absolutely. This is all enabled by this ORAN and virtualized RAN architecture, because you don't have to deploy everything upfront on the cell tower, right? You can have a sort of a data center somewhere, a small data center somewhere, where you have certain computing resources that you can share among the different cell sites. So one cell site is, if one RU, right, has no users, it doesn't need any computing, right? So you can shut off some of the computing power, right, to save energy, or you can give this computing power to other RUs to do, I guess, maybe more iterations or better signal processing. Yes,
Yeah,
absolutely.
thank you.
This is the beauty of this. It was already possible with the virtualized RAN or Cloud RAN.
And may I
Okay.
ask, is
Yeah.
virtualization, I'm not sure, is it work for, especially for URLC traffic too? Because I mean, virtualization and move the resource from the other part to the other, and for URLC like traffics, is it work for this specific traffic too, or it's more work for the other kind of traffic that we have, at least not restricted line for us?
Yeah, it's a great question. Yeah, obviously virtualization adds a little bit of overhead, but in principle, it's just kind of the how you deploy it, and how much, I guess, you need a little bit of overhead in terms of mostly storage and CPU power, right? Um, I think it can be run in real time. It doesn't matter which service you use. So you so the virtualization part is not mandatory. It's meant to be virtualized, right? But it doesn't have to be. And I guess whoever implements this ORAN is by default virtualized, right? It uses virtualized service, but the RAN itself, it doesn't have to be necessarily virtualized. So it
That's right.
depends on the operator or provider, right? But I think it can be done. The only thing is you need a little bit more resources, right? It's not as optimized as obviously building it on hardware, right? But
Yeah,
on an ASIC, that's the best, most optimized from in terms of energy, right? And chip size, etc. But it's the least flexible. So because now CPUs and GPUs and other processors are so powerful, right? You can afford the
yeah,
extra overhead.
absolutely. Yes, thank you. Thank you, sir.
You're welcome. Great questions. If anybody else has questions, just interrupt me. So to
Hi,
sum
sir.
up,
Yeah,
yeah,
sorry to interrupt you. You mentioned like we can have sort of a data center that can on demand, by demand, provide more compute power. So that would map to like OCU or like ODU. Can you clarify that a bit?
Yes, you're right. It doesn't help the ORU, right? It can only work for the OCU and ODU, and you need to be careful with the data center, right? You cannot, because of the latency that is introduced, right? You cannot do the cloud per se for real-time signal processing, right? The cloud can be anywhere, right? If you use this Teams meeting or Gmail or anything, right? It's on the cloud, and it's not really necessarily at the real time as per the cellular traffic, right? So it cannot be at any data center. It needs to be somehow localized for the DU, right? And can be more centralized for the CU. And um, that can be like a data center specifically built for the RAN, not a general purpose data center that is being used for anything in computing. Does it make sense?
Yes, but if so, like if it is say more towards the OCU, then we are limited by the mid hall and the front hall, and if it's more towards the edge, then like we cannot really put data centers on the edge, right? So
That's right. Yeah, you don't need a data center there. You can do uh, any computer, put any computer there or edge server, right? It could be an edge server where the ODUs run or where an ODU runs. You're right. It doesn't make sense to implement the data center here for the ODU. It's too costly, right? And you don't need it. So this is something, yeah, this is something this can be researched, I think. If you ask me, I think the operators won't deploy data centers. They will just deploy some servers in a server rack, right? Somewhere like they did before. But instead of putting it next to the tower, they will put it in some strategic place that serves for the DU, right? That serves multiple towers. You know what I mean?
yeah, like
Yeah, go ahead.
they also have to like because of the distributed disaggregated
Yes.
approach, like because of the densification. So they'll have to, I guess, distribute more of these racks and servers. It's really,
Oh, that's a good
yeah,
question.
it's
So
hard to, yeah, I mean, sorry. I was just trying to say that that with this densification, like, I mean, there's a limit to how much hardware you can put in like near the edge, right?
yes, but think about it as, let's say you have I don't know, 50 kilometers range, right? A radius of 50 kilometers, for example, or 20 kilometers, right? And you have a lot of cells, let's say 100 cells, 100 antennas, right? 100 RUs. And in the middle of this radius, you put your mini data center there, or edge computing site there, right? And you can build a small house or cabinet and put in one rack, right? With let's say 5 servers, for example, right? And if you're densifying the network and deploying more RUs, you need more processing, right? Hopefully your house is big enough, you can add another server rack, right? With another 5 servers. That's the
Okay.
idea, as opposed to going to each antenna, right? To each cell site, each tower, and add a new server or new rack into the cabinet. So you somehow you do centralize it somehow, because one DU can serve many RUs.
Mm-hmm. Yeah, that makes it clear. Thank you.
Thank you for asking. I'm glad that you asked. Maybe having this discussion. So to wrap up, so these xApps and rApps, they done run at different time scales. I mentioned that, and they, as you know, when you talk at the lower time scales, you may be managing a single device, right? If you go to higher time scales, you manage tens or hundreds of thousands of devices, right? This is just how the RAN operates, the regular RAN. And now we have the RICs and the xApps, right? They can what this figure shows is xApps can affect several devices, let's say hundreds of devices, but rApps can even affect more than that, like thousands of devices. So maybe I can go through this real quick because this is just what the interfaces look like. So there's also a notion of OCloud, which I don't want to talk about much today, which is just an ORAN cloud where you can maybe store some new functions, etc., and use them later. But as we said, we have the service management and orchestration framework connects to which has the non-real-time rig. The non-real-time rig needs to talk to the near real-time rig to exchange information and data. And in these two rigs, we can have AI, right? And then we have the RAN on the bottom, which has the 3GPP interfaces, the green ones, and the ORAN interfaces, which are the red ones, which are specifically developed by ORAN. They're openly implemented, so anybody who implements those interfaces can, in theory, right, communicate to each other. So one ORU built by one vendor can communicate with another ODU developed by another vendor because they both implement the interface the same way. Okay. So because we have more interesting things coming up, let me go real quickly through there's Open Front Haul, which splits the DU and RU, right? It uses the enhanced common public radio interface, which is very common since 4G, or maybe even before. Then we have the F1 interface, which is an 3GPP interface. It is between a DU and CU. Then we have the E2 interface, which is very important. The E2 interface connects the near real-time rig, or the xApps that run in a near real-time rig, to the RAN. And I'll have a slide on this in a minute. We also have the A1 interface. It helps the non-real-time rig and near real-time rig exchange data, so data parameters. Imagine you have an AI model. You can have the AI model being trained in a non-real-time rig while you're collecting data and training it, right? And then you can pass the model parameters to the near real-time rig over the A1 interface, and the near real-time rig then implements this model as an xApp. And then there's also O1 and O2 interface at a higher layer here. So in the interest of time, let me just go through some of the important interfaces, which is like E2. So the E2 helps the rig collect data from the RAN and also control the RAN. So how it works is it's specified. This interface is specifically specified by the working group 3 from ORAN Alliance, and it provides you E2 related procedures and information elements. And this is all encapsulated in the E2 application protocol. So as E2 messages are comprised, E2 messages that go between the near real-time rig and go between the RAN, they are comprised of one or more of these information elements which define the content of the message. So it's like a message passing protocol between the RAN and the rig that carries messages such as set up the connection, update the connection, and also these are called service class procedures. But then there are also support class procedures, right? You have support class procedures to set up the connection, and you have service class procedures to actually send some actual data from the RAN, like KPIs, key performance indicators, and also receive control indicators from the near real-time rig to set up the RAN accordingly. If you look at this from on the left side is the near real-time rig, has a bunch of services, and one of them is the E2 manager. And the right side, we have like an E node B or G node B, a 4G or 5G base station that is implemented disaggregated way. So it has an E2 agent. So these two, E2 manager and E2 agents, they establish the connectivity and E2 interface protocol. It uses the stream control transmission protocol over the E2 interface to exchange information. And we need to, each RAN node, so each DU in a sense, needs to register to the rig, right? So that it can provide data and get some control signals from the rig. So first of all, the connection needs to be set up, right? And then E2 sends a request message, includes a RAN ID, and then there's some security being involved to check that this valid RAN ID. And then the E2 termination receives here on the left side, receives the messages or requests and forwards to the E2 manager, right? And which then decodes and authenticates the RAN node, and then can actually send back an acknowledgement, and then actual real data can flow, right? What is this data? As I mentioned, the key performance indicators can be packaged and reports and sent over the E2 interface from the RAN to the rig. And the rig uses this information to see if the RAN is operating efficiently, right? And maybe it realizes that certain RAN nodes or certain cells are overloaded and others are underloaded, right? And tries to do some load balancing, for example. All right, let me skip this, the interfaces, in the interest of time, and briefly introduce the ORAN Alliance. Like the 3GPP, right, the ORAN is formed out of industry, and those are the same industry members that belong to 3GPP. AT&T, China Mobile, Deutsche Telekom, NTT Docomo, and Orange were the founders of this ORAN Alliance, which nowadays, of course, has many more partners. Even academia can be a partner. So what they do is they standardize this ORAN framework, architecture, services, etc. What is their scope is to reshape the RAN industry towards intelligent, open, virtualized, and fully interoperable mobile networks. So this is the main goal of ORAN Alliance, to walk away from proprietary cellular networks to open radio access networks. So they have specifications, they define the interfaces, etc. There's the ORAN software community that provides some software that you can use and build your ORAN system. And it has test and integration, so how to test these ORAN systems. So as 3GPP, ORAN has a lot of working groups, each dedicated to a different piece of the architecture, right? There is the use case and overall architecture, non-real-time rig, near-real-time rig, etc. You can see a little diagram here. And of course, there is security as well. And then there's some focus groups. They are looking into, I guess, the more contemporary features or future features of ORAN, like or simply holding the organization, like developing the standards, right? Or open source focus group, sustainability focus group, about energy efficiency, industry engagement focus group. So they're trying to grow the system and make it popular and deployable in the future. Any questions? Any more questions about ORAN? And I realize that other speakers are also talking about ORAN.
So far, so good. Thank you.
Thank you very much. If you need the slides, you can let me know. I can share them as well. Okay, let me talk about our project OpenAI Cellular. It's a platform, an open platform, including software, library, tool sets, and documentation for prototyping and testing AI-based RAN. So because 6G doesn't exist yet, so we are essentially assuming 5G RAN and introducing AI to it, right? It is based on ORAN architecture interfaces. And it's a project that started a long time ago. So how did we do it, right? We used open source cellular software like SRS-RAN and OpenAir interface, OAI, and also simulation platforms to simulate the RAN. We use the ORAN software community's code. They have some software code and integrate it into, let's say, SRS-RAN and OAI. And we use software-defined radios, mostly USRPs, to build a test bed that actually can execute an ORAN system. So why do we do this? Well, you know, AI is quite popular nowadays in all facets of our life, right? It can also help in wireless. It can help with beamforming, scheduling, spectrum sharing, and so forth, right? So we can use deep learning or other machine learning technology, right, to optimize or develop different types of signal processing methods as opposed to traditional DSP. So what are some of the challenges of using AI in a RAN? Well, while it's promising, there is no real world, there are not enough real world experience at scale that uses AI in a cellular world, right? It needs to be extensively tested, and it needs to be provided for researchers like you, so you can actually test your innovations of how to use AI in cellular, right? So what are some of the key research questions? So how do we design a cellular network to be more AI suitable? And where should the AI be, right? Should it be at the core, at the RAN, or which function should it replace or optimize? What kind of methodologies can be applied to test the AI performance in a at-scale network? How do we test cross-layer interactions of AI deployed at various points in the network, right? There can be an AI at the scheduler, and it can be maybe AI at the beamformer, right? And how do they interact? And how do we find the right configurations and configuration failures? Maybe we can use AI for testing as well. So this is what motivated us to build this OAIC platform. It is a software platform that can be deployed on a software radio testbed to do AI-enabled RAN research. So everything I told you about ORAN is what OAIC embraces. It has the near real-time rig, it has the RAN, right? It has SDR, so you can do over-the-air experiment with AI involved. So OAIC has two main blocks, the AI controllers and AI testing. So now for the next hour or so, we're going to talk about AI-enabled cellular controllers or the framework itself. And later, if we have time, I'm going to talk about the testing, how we can use AI for testing. So what exactly is OAIC, or what exactly do we mean by AI cellular RAN controllers? Well, we use the ORAN architecture, right? We don't invent a new architecture. It's an industry standard. We use the 5G NR protocol. There is no 6G protocol yet. Maybe it's coming up, but it wasn't when we started. And we use software radios that everybody can purchase, right? And use. So we have on the left side, what you see here is the non-real-time rig and a near real-time rig on the bottom with its interfaces and components. So we don't have the non-real-time rig, the green box we don't have. We do have the near real-time rig where the xApps ran and control the network. So then we use SRS RAN and OAI for the RAN itself. Maybe you heard that SRS has a new project called Okudu, so we can use Okudu in the future. And then importantly, we also have the E2 interface, right? The E2 interface connects between the near real-time rig and the RAN itself to be able to actually do something about the RAN, right? Receive information about the RAN and send some control messages to the RAN. And then we can use SDRs to actually build an over-the-air experiment, right, with commercial off-the-shelf UEs or with SDR UEs. So as I mentioned, for the disaggregated RAN or for the RAN itself, we use SRS RAN. We also offer open air interface. For the E2 interface, we use ORAN software community specifications and software to implement it, to connect SRS RAN to the near real-time rig. For the RAN intelligent controllers, we use again, for the RAN intelligent controller, we use the near real-time rig from the ORAN software community. And we wanted to do some real-time extensions, so we do some AI at the RAN itself. And we have a lot of xApps that we developed or used. And then for the core network, we simply use Open5GS. So the RAN and core are given, and we integrated the E2 interface and a near real-time rig from the ORAN software community. As I said, we implemented a near real-time rig from the ORAN software community because we did this a long time ago. It was compliant with the E-release, which is now dated. For the cellular stack, I mentioned we use SRS-RAN and OAI. And for the AI-driven controllers, well, there were some xApps that were available from industry, developer industry, which we integrated. Also some from other universities in the US and around the world. And we built our own xApps, right? For example, we implemented reinforcement learning based on mission control and scheduling xApp. Or we also developed a test xApp that looks at the xApp performance. A lot of xApps that we developed and published in different papers. And some of these xApps we will present to you in a few minutes by means of demonstration videos. And everything is open source. There is a website called openaicellular.org that hosts all these things that are available to you. Let me see. Also, we have, okay, sorry. Also, we have OIC is a community software, right? So it's fully open source. It's available on GitHub, and it also allows you to contribute to it. So we have three main areas of development. It's easily accessible source code on GitHub for developers to try. So you developers or researchers, right? It's free open source, community driven, and based on open tool chains. It's also easily deployed on target hardware with minimal effort. So you can download virtual machines if you want with the latest verifiable source code and connect it to your testbed. You can also contribute to it easily because we provide you the common development cycle. You can fork, commit, or submit pull requests. You can also deploy OIC in the cloud. Obviously, you won't have access to USRPs in the cloud or SDRs in the cloud, but you can run it with virtual radios, right? In, for example, zero message queue. So we can install it on a virtual machine or container or bare metal. It's your choice. You don't need to have an SDR testbed or access an SDR testbed. You can run it, for example, through zero MQ. And we also have a bunch of things that help you, that help us or you test the code. We use GitHub Action workflow to verify full installation and execution. So whatever code you pick from our website has been tested from our repository, has been tested, and you can use it for your experiments. So if you want to contribute to OIC, please do. You can develop your own xApps, you can develop new features, right? You can try another RAN or integrate a simulator if you want. What you need to do is to you need to submit a pull request of whatever you developed, right? Maybe you just integrated a few more lines of code, or maybe you integrate a full new RAN or a new xApp, right? So you should provide us with tests that cover how this functionality works. And then we run it through the pipeline to make sure it doesn't break anything, right? We have a CI/CD pipeline, and then we will accept your pull request. And if there's a problem, we let you know. So as I mentioned, OIC is a platform. It's a software platform, but it's not meant to run in pure simulations, right? It can run, as I said, with software radios. I see here on the top a bench with the computers and SDRs. And we definitely want to scale it across larger platforms, like Virginia Tech has the Cognitive Radio Network testbed with a bunch of USRPs deployed in building. And there are other platforms in the US called Platforms for Advanced Wireless Research, which offer you essentially SDRs to access if you're an academic for free to do your experiments. But I'm sure there's some in Europe as well, and maybe in your lab. So you can try it with your USRPs. So finally, we have a website. This is the starting point. It's called openaicellular.org. You can send us an email. We have a code repository. Everything you can find through this website, openaicellular.org. We have a YouTube channel. You can watch videos of what we like tutorials and videos of some of the experiments we did. And you can join our user group, our Google groups, to get updates about this project. So this is it for now for me. Do you have any questions about any logistics or anything I said? If not, Josh is here. Josh is a PhD student at MSU. Josh, are you ready?
Yes, Professor.
Yes, we can hear you perfectly. I'm stopping to present, and you can present now if you're ready.
Great. Thank you so much. How's everybody doing?
Hi, thanks.
Fantastic.
Hi.
Thank you so much for letting me speak this morning. I'm going to minimize the screen, but if you have any questions during the presentation, you can, of course, just interrupt me. Can you see my screen pretty well?
Yep.
Yes.
Yeah, we have.
Okay, great. So my advisor, Dr. Merjovic, just gave you a kind of introduction to the OpenAI cellular platform, of course. I think he did a very well overview of the platform. But as a PhD student, I hope to give you a more kind of practical view of how you might use the platform for your own research, as well as sprinkled through, I thought I might give you some kind of insights on how it was to develop for the OASC platform myself and some of the challenges that we faced so that it might help you. So that's what this talk will be about for the next 40 minutes or so, kind of deep dive into the platform, how you might deploy the platform for yourself and use it for your research, as well as I have some video demonstrations of some xApps that we've developed over the last couple of years that I'd like to show you as well. So as Dr. Vuk introduced me, my name is Joshua Moore. I am from Mississippi. And I attend Mississippi State University, where Dr. Merjovic is my advisor. Since I've joined my PhD program direct from my undergraduate, I've published 14 papers, mostly focused on security and ORAN and the intersection thereof. And as we move towards 6G, I'm focused more on automated security testing of RAN, as well as AI RAN and that intersection there. So in today's talk, I've kind of broken it up into 4 discrete sections here, as you can see. First, I'll kind of give you a platform overview. I think Dr. Vuk did a pretty good job, so I'll try to make that pretty short and sweet and cover anything that I think he might have missed while I'm there. And in the second part of the presentation, we'll go over the documentation and the software of the OpenAIC platform. And then third, I'll give you the xApp demos. I'll try to spend the majority of the time that we have together today talking about those demos, so that if you have any questions practically, you could ask me. And then in 4, I'll kind of briefly go over something that I think is still pretty unique about the OASC platform is that we give you all the documentation and software tools to build your own xApp. So that's based in Python, and I'll go over that documentation as well. So as Dr. Vuk mentioned, OpenAI Cellular is a community infrastructure built for the purpose of prototyping these AI-based controllers in the ORAN architecture.
Yeah.
Hello, did you have a question?
I sent for all of them.
Can you hear me?
Yeah,
Yes.
we can hear you. It was someone who is not muted.
Yeah. Oh, great. Sir, if you could just mute yourself.
Okay, that's okay. You can keep going.
Okay. So I'll kind of use that to pose a question to the audience then, if I may. So whenever I started my PhD at the end of 2023, going into 2024, OAIC was my first project. And we know that going into 6G, this AI RAN is really the main thrust and exciting feature of 6G. So what do you think it might have been like in 2024, early 2024 for a researcher trying to build these xApps or prototype AI? So that, go ahead. It can be somewhat rhetorical then. So it was like a wild west, if you will, right? So early on, we had so many problems of bringing up ORAN software community RIC. There was just missing software that we had to write. There was not any functionality for xApps. So really, this project and when I joined was really the first kind of effort towards bringing a community-driven infrastructure and making it easy for researchers like ourselves to deploy and prototype xApps. So really, that's kind of the key feature early on that OEIC brought to the community of making it easy. And I'll tell you right now, we had such a hard time, especially getting a compliant E2 interface working or prototyping those early xApps that I think will be lost in the history. But that's for sure one thing that happened. So anyways, I digress. OAIC, as you heard before, is made up of these two discrete components, OAIC-C, the controller framework, and OAIC-T, the equally important testing framework therein. And of course, we have the website, which is kind of the main place that you could go to get all these different links at the top here. Practically for us, the most important link that I use a lot is the documentation, which we build through the CI/CD as well. So that is updated by the community as well as us when bug fixes come through the pipeline, as well as you have the code and the videos there, and then the community in the mailing list and the YouTube as well. So as far as the features, of course, it's made up of these three distinct components. You have the near real-time RIC, the cellular stack, which we use different community software such as SRS-RAN and Open Air Interface. We have both non-standalone and 5G standalone support, as well as 4G support and virtual USRP support through the 0MQ message pass interface. Also, we have the ability to use GNU Radio to broker connections for multiple USRPs virtually. And we prototype many EDIS USRP devices as well with this. So there's the important SDR support. As far as the xApps that are supported, this is not an exhaustive list that I'm sharing with you on the right here, but these are the kind of ones that I'll go through today. We have the KPI monitoring, RAN slicing from Powder. We have a secure slicing xApp, and we have an intrusion detection and some large language model xApps as well. So practically, what are your deployment options if you want to get started with OpenAI Cellular? Well, I'm proud to say by no small feat that we have 4 different options for deployment. So of course you have the bare metal deployment. You can install Ubuntu, which is an open source Linux operating system. Either Ubuntu 20.04 or 22.04 is supported right now. Of course, we try to support the latest LTS release, but from a development standpoint, that's a little bit difficult as we're based on a Kubernetes one node deployment. So we have to version that to the newer versions to support those newer releases. But usually, if the community has support for the newer release, we'll get a pull request and support that. On the right, you can see that we have virtual machine support. I see a lot of people go in this route. So you can use the common virtual machine software to get Ubuntu running on that and deploy it through that. We have specialized scripts for the virtual machine deployment to make sure that the performance is going to be up to snuff inside the virtual machine so that you get full sample rate, especially at the cellular stack level. Down at the bottom left, you can see that we verified it on Google Cloud and used this successfully in our 2024 workshop. There's a pretty great free tier option for Google Cloud to get started with that you might want to prototype it on pretty quickly. And then we've also verified it on the Powder testbed, which is a community testbed in the United States as well. So here in a minute, I'll bring up a video to show you, I'll kind of skim over it and show you the kind of typical ORAN software community deployment. Of course, we have two different deployments there. We have the ORAN software community deployment, meaning that this is their release of the near real-time RIC, and we integrate that with the cellular stack, whether that be SRS-RAN or OEI thereof. And we also have the kind of OEI variant where they have their own Flex RIC, near real-time RIC, if you will. And that is not ORAN software community compliant, but we still offer it to the community. So the default installation is the ORAN software community installation. As you can see down there, it starts with you provisioning your machine, whether that be VM or bare metal or the cloud. And then you have this K8s cluster. We deploy a one node cluster by default. Of course, you can edit this to distribute this cluster across many different nodes. And we provide a pretty easy spec for that. And then, of course, the third kind of larger step is to deploy all the different microservices of the near real-time RIC inside that one node cluster. So if you can see here on the left, this is all the different microservices that I'm going to show you here in just a second. That would be part of the near real-time RIC. We want to make sure those services are up and running before we proceed to onboard any xApp, because these are services that we need for all of this to work. So now I'm going to kind of switch to a couple minutes of a video of an undergrad that we had installing the platform. And I want to kind of touch on a couple of things here. So I want to get this full screen and mute it. And can you still see this video?
Yeah.
Awesome. Thank you so much. So as you can see here, the typical kind of way that we like to tell people to get started with the platform is to put the documentation from the website there on your left-hand side of your screen. And then on the right, I like to have a full screen terminal here. And then it's more or less just copy and paste. We've tried to do a job of kind of explaining what all the different commands are. And this has been tested through the CI/CD, like I said, so everything should be able to be copy and pasted pretty low effort. There shouldn't be any kind of unforeseen problems at this point, I would hope. But of course, if there is, you can always open an issue and we'll get that closed pretty quickly. But as you can see on the ribbon on the left-hand side here, you start from the installation procedure. It'll go through all the different requirements that I just talked about. And then what's happening now, of course, is it's cloning down the repository. And the main repository, I won't get too technical, but what we do in the main repository is we make submodules for each different component here, as you might can see on the right-hand side here, so that we can version control each different component. So all the microservices are in their own repository, and then when you clone down the main OAIC repository, it actually brings down all those at the version that we deem working at the time. So that gives us a little bit more control over the software here. I'm going to kind of skip past this a little bit. Oh, well, this is going to the next part. So at this point, we're going into the K8's directory inside the main RIC deployment directory here. And what this is going to do is it's going to deploy some base services that we'll need. And this GenCloud init will set up this one node cluster for us that I alluded to earlier. We actually use the Kubernetes version 1.16, which is an older version of Kubernetes that we actually maintain for the community now because of the software. So we've had to pull in that dependency to our own repository because upstream they stopped supporting it. So as we version towards a newer LTS, this will deprecate, but that's one of the challenges that we had for sure, because they like to move pretty quick with the Kubernetes releases, and we weren't comfortable moving that quickly. So this script here, the K8's one node cloud init script that just runs, this actually bootstraps and automates the entire process for you. So this is going to first install all the dependencies that you'll need. So if you notice, I didn't ask you to install Kubernetes. I didn't ask you to install any Python dependencies or anything like that, because this script, K8's one node cloud, will actually do that for you. And this script will actually figure out which version of Ubuntu you're using between the two that we offer, and it'll go ahead and pull in the dependencies for that specific Ubuntu version. Again, if there's any questions, just interrupt me and I can go over more of that. But like I said, this will set up everything and automate it for you. And then once this script gets done, we can go ahead and check that all of these base pods are up and running. I'll kind of skip ahead a little bit. As you can see here, we're kind of waiting for all the different pods to get up and running so that we can kind of proceed with the near real-time RIC pods in the next step. So they're all running now in this video. And then we'll create the namespace for the RIC infra. And then we use Helm, which is of course a package manager for Kubernetes, to install in that namespace. We're actually installing it for the storage right now. And then in the next step, we'll use a script similar to that script to install the near real-time RIC and all of its components. First you would build the E2 Docker image. So we provide this image of the E2 locally, and then you can either build it or you can actually pull this down. We do have a Docker Hub version of this, but it's a pretty small image, so it's usually not a problem. And then of course you'll push it to your local host registry. So this is the next script. It'll deploy the near real-time RIC automated for you. We base this script, as you can see from the kind of syntax that we're using here on the string, based on the release of the ORAN Sulfur Community RIC. This is at this point, a pretty old release in this video. This is the E release of the near real-time RIC. And the release of the near real-time RIC, I don't think that was touched on, but basically what happens is the near real-time RIC, of course, is constructed of these different services, and the release is indicative of the different versions of those services within the near real-time RIC. So of course, like the E2 manager will be bumped in a different version as opposed to the database used, the database services or what have you. So the e-release is deployed here. Again, this is a fully automated script for you. You can read through this and figure out what each of these are for, but the main thing to see here is that you have this deploy RIC platform script, which is called with -f. So it's waiting for this recipe file. You can go into the recipe file and see that all of the services are listed in a JSON structure. So you can actually modify this release file based on your needs if you wanted to have a different version of a software. Or you can bring your own recipe file from ORAN software community and have a newer release if you'd like as well. And that should be pretty easy to integrate downstream with the cellular software stack, whether it be SRSRN, which has their own support for the newer releases of ORAN software community at this point, or OEI has actually been prototyped with an ORAN software community RIC at this point as well. Actually, I think they bridged that integration through their FlexRIC. So you would bring up the FlexRIC and then that integrates with the ORAN software community RIC through a custom interface that they have. But like I said, I don't want to get too technical here. But this is a kind of basic installation from a practical standpoint that you would see. One thing left to touch on here is when this script gets done, one thing that you'll see is that the E2 interface service will be the last service to come up. Usually we have to wait a few more minutes for that one to come up. So you'll see that. Okay. So the next video demonstration that I want to kind of give you is this KPI-Mon xApp. And what this xApp does is it's deployed into the near real-time RIC, and then it captures these RAN KPIs, whether that be the signal to power ratio, the throughput, the signal to noise, RC state, and then many more custom metrics that you could or we have enabled. Today, I'll actually show you the OEI and FlexRIC variant of the KPI-Mon xApp through a demonstration, which I'll do right now. But I want to kind of stress the importance of having a KPI-Mon xApp because KPI-Mon is usually kind of, there is a Hello World xApp, but this is usually kind of the jumping off point for me whenever I'm building a new xApp. So we like to start with having all those metrics that we would then use to train an AI model or what have you. So in OEI, they have a little Python script similar to what we had. In this video, I've taken the liberty of already having it pre-installed here. But you would start their FlexRIC with this start near real-time RIC. And then the last screen, you saw that they were starting the OEI GNB. And that near real-time RIC interface will interface with this. And you can see that it's accepted these RAN functions. So what happens is when you start the GNB and the near real-time RIC, the near real-time RIC or the FlexRIC will look for all the different service models that are enabled at the RAN. So what this means is it'll subscribe to these different service models, and whatever service model that it subscribes to is the functionality that could then be enabled by an xApp. So as you can see here, they have different IDs for the different service models. And for this specific instance, this is all the metrics that they could actually get from this. So here we'll connect a virtual USRP. As you can see, we've established a PDU session, so we have data flow. And then we'll just exchange some information across that, so we have some traffic. And then as you can see here, we're using the C version. They also have a Python version, since FlexRig allows for the cross compilation of their code between C and Python and other languages as well. They use Swig, which is kind of a library to help them do that automatically. But as you can see, when they run their xApp, it's kind of a sequential code. So it's not a loop that happens. Rather, they have a step-by-step in their code. So all this is going to do is make this RIC subscription request and then start to collect these metrics that are enabled by the service model that you had seen previously. And by default, this xApp doesn't save this information anywhere. It just prints it to the screen. And as far as I saw last time I ran this, which was about a year ago, a lot of these values seem to be kind of erroneous. So if you plan on using this as a base for your research, I would make sure that these values are real, of course. So again, the kind of thing that I want to stress on here for the KPI mon is that I start usually myself with a KPI mon base, whether that be through FlexRig or SRS-REN, and then I would build my functionality based on some metrics that I collect. And that's a common workflow for the community actually at this point. So the next video tutorial that I want to talk about is one that I did like in the first 2 months, I think, of my PhD, is I took a slicing xApp from Powder, which is the community testbed at University of Utah. They had developed this per slice PRB scheduler, and then a corresponding xApp that controls that scheduler through different allocation policies. So they were able to show proportional scheduling through the slicing xApp, or they were able to throttle users. So this is kind of, and so they were able to show different policies through there for the scheduling. As you can see here, this is kind of the deployment of this. This uses SRS-REN eNode B, so it's based on 4G. And then it uses a REN software community RIC. Powder was actually instrumental early on for enabling some of this community infrastructure of the REN software community for the broader community, such as, for instance, they were the ones that actually wrote a lot of the scripts that would then be evolved into OEIC platform. But NextRAN is deployed like any other xApp. There's a corresponding schema file for the xApp, and there's an onboard URL. Let me go explain that. So here we specifically build their E2 version of SRS LTE, that 4G. As you can see, I'll go through that. But the important thing here is that they compile their bindings in with this SRS LTE E2, as you can see here. So there's a E2SM KPM, which is the service model. This is these two files, and then there's an E2 AP, or the E2 bindings that are compiled in with this SRS LTE E2. This is something that you don't really have to worry about at this point, but at the time, this was something custom that they were doing. So I'll kind of skip past that. So ASN1C is a compiler that you still need at this point. It's for the interface. And none of this was automated at this point. So it's still going through that software installation that we were talking about. And here we'll build the NextRAN. It's all Dockerized, which any xApp will be. So we'll clone down the NextRAN repository, and then in the next one, we'll tag that Docker image with the NextRAN name and put it in the xApp registry. And here in a second, I will get to running the xApp. Okay. So this is starting a 4G core network here. I'm using tmux to multiplex this terminal. As you can see here, the RIC has established a E2 connection to the RAN, and we'll connect a virtual USRP using SRSUE here. We use iPerf to exchange traffic from that UE. And as you can see, I forgot to install iPerf at this point. So I'll go get that. And as you can see now, we're establishing a connection to the ENB from this UE, and we're exchanging the traffic over it. So this is an important step here. What we're going to do is we're going to export all of these different variables into our shell so that we can use them to onboard our xApp. And once the xApp's onboarded, which we give these curl commands, which makes a HTTP request to a Prometheus server, you can think of it just like a local server so that we can host the xApp. And then once we do this command, you can see that we actually deploy the xApp successfully, and the version of that xApp that's deployed. I'll get Kubernetes to tell me if that has been successfully deployed and it's in the running state. And now that's in a running state, what we'll do, NextRAN actually enables an interface to the user. First, we'll look at the logs of the xApp, which is common to any xApp. So as you can see here, the RMR is giving us the messages, and those are going to be important to look at the logs for any xApp as you're running it to try to debug or try to see what your xApp is doing. Of course, because it's a container, so you wouldn't have this kind of easy visibility to what it's doing. So the way we'll do it, because there's a lot of different things that will communicate to NextRAN to get it to show a demonstration of its capabilities, is we've gone ahead and scripted these different commands. So what it's going to do is it's going to set up a virtual node B and some virtual slices. There's a fast slice, and there's also a slow slice. And what I mean by fast is a kind of default full bandwidth that we have going here in the left top terminal, and then kind of slower throttled slice. And what's going to happen is we're going to slice it from the fast slice here, and we're going to update it and post it to the slow slice. So you'll see the throughput change in the top left corner. And this was around 2024, mid 2024. We successfully ported NextRAN over, and I know a lot of the community ended up using this, as well as I did for my own research. So you'll see the share of the resource block change, and you can already start to see it dipping, I think, here. Yeah, it'll go down. This is based on a proportional share scheduler. Of course, there's only one UE here, but if you had another one, it would try to balance that throughput disparity between the two, even if it was moved to a different slice. So as you can see here, the xApp did what it was supposed to do, which at the time was a kind of magic thing. Of course, it's been some years. So that's this xApp. It's slicing the resource blocks. You can do some fun things with this one. So the next one is kind of an xApp that is in the FlexRAN. Oh, by the way, Dr. Book, I think I'm over the time already. Do we need to? I don't know when we need to take a break, but if you'll just let me know.
Actually, it's up to you. I mean, it's at your convenience. If you want to do the break right now, it's okay. If you want to continue and do the break afterwards, it's also okay.
Okay. So if it's all the same, then I'll just continue and we can do it after.
Okay.
Thank you very much. Okay, so the next one is a RAN control xApp. This is an OEI demonstration. They're using their FlexRIC. What this xApp will do, and I'll actually let Pratik, which spoke at our workshop in 2024, he gave a great presentation of this xApp. I'll kind of let him narrate this video. But what this does is it sets up a DRB context, and this way we can control the different quality of service via these E2 control messages that would be posted. So this is a way that you could, for instance, kind of partition one throughput to an EMBB throughput target and one to a lower. It is not slicing, but it is this quality of service flow that's enabled in 5G through this DRB. So let me bring this up. And as you can see, he talked for like 3 hours. So we are going to go, I think, to 121, which is where he starts to talk about this. So this was an interactive workshop that we had. So I'll try to skip past a little bit here. But people came and it was a very hands-on session, and that was a great session where we worked with the community to show them what we had done up to that point.
Ferran, do we need to do a break?
If you want, yeah, we can do the break for half an hour.
Okay.
Is it okay?
Josh, is that okay?
Yeah, sure. So, um, with this video, you've already seen what was going to happen. Basically, the KPI I'm on is given the metrics, and then it'll issue a DRB to release the UE, which it did. So after the break, what we can do then is we can pick up with the next demo. And there's 2 more demos, and I'll talk about developing your own xApp after the break, okay?
Okay, thank you very much, Josh. So the break will last around 30 minutes. So see you then, okay?
Okay,
Thank you.
Sounds good. Thank you.
Thank you. Thank you.
Thanks.